Hello and welcome, chapter number 1. Oh, in my case it's right 0, but never mind. Okay, let's start. Like and usually, we need import libraries. In Python, it works like that. So I use quite general libraries. I believe that's now everyone who works with Python language. It's Matplotlib, Pandas, Snipey, Scipy, MNE. Okay, MNE probably it's not so general, but I will talk about that a little later. So, okay, now in the first I need to connect to my Google Drive to receive access to dataset. Yes, it was successfully done. Okay, so import libraries. And yeah, in the first MNEs, it's not so general, it's necessary install. You can do it via the next line. Okay, move forward. In the next one, it's necessary import datasets. I used this one by EEG device. I use it for collect datasets. It's just only Shield, that's allow convert Raspberry Pi to brain computer interface for 16 channels. In my case, I use just only 8 channels. Electrode were located according international EEG locations. So you can see in the map how it looks, which position for electrodes was used. Okay, the next one, it's necessary import our dataset to Google Drive. It looks something like that, 8 channels, raw data in microvolts already. And the next one, let's make some visualization for raw data. I use it channel number 1, here write 0, okay? And it looks something like that. It's especially these datasets, it's quite noisy, but it was done specially, really, because I wanted to receive much more noise dataset, because in this case, we can use much more clearly our signal processing knowledge. It's why it's noisy, because it was not so good connection. It's, let's say, mechanical between electrodes and the skin. It was not so forced, just only slightly touch my head, let's say. Okay, next one, it's a bandpass filter. I will not so much pay attention in the current moment, but what's the bandpass filter, I will consider it in the next chapters. Just only would like to say that I use it. Okay, yeah, it's just only to remove any noise, and we can choose which type of frequency we would like to demonstrate. So it was implemented, this one also. Okay, bandpass filters, if you use frequency from 1 to 50 Hz, it's EEG data looks like, and raw data just only without fluctuation. But if we will remove 50 Hz, especially noise from electromagnetic, from power source, let's say, and put something like 10 Hz, it already will be, looks much more better. And yeah, it's something like that. And generally, yeah, I didn't say it, but this dataset represent Turing artifacts for 3, 2, 1, and blinking artifacts. It looks much more smaller, but exactly the same. It's 4, 3, 2, 1. So, and anyway, it's much more visible already in the current moment after bandpass filter. And implement a bandpass filter for all datasets. And again, the same structure, 8 channels, and just only in columns, data for all datasets. So, and yeah, I didn't say, but it's a quite important moment. How to convert a dataset from digital to microvolts, because PyG use ADC1299 analog digital converter from Texas Instrument. It's 24-bit resolution. So we receive digital data, this one, we necessarily multiply for 1 billion. It's because it's moved from volts to microvolts, let's say. It's 4.5. It's a reference voltage, what was used in PyG device. And divide for this value, it's just only 2 to the power 24. And finally, we already receive microvolts, what was done here. So let's move forward. The next one, what we can do is our data for visualization. It's EEG heat map. Generally, it's quite useful because, it's, for example, in this case, we can use 8 channels on the left side and EEG amplitude on the right side and time. So, and it's quite clearly visible that we have tuned artifacts here, 4, 3, 2, 1, and blink artifacts. For one channels, how we can see, for example, blink artifacts much more visible than Turing artifacts. And generally, it's This image also can be used for deep learning, especially convolutional neural networks. This image can be used as input for your model, but we don't consider in the current moment in this course. But let's move forward. It's a 3D graph. It's also quite useful because we can see all data set in one graph. We can see correlation between which channel is much more sensitive for some artifacts, let's say. And also, it's quite useful because, for example, here we can see that in the channel number one, when we start just only measurement process, it was some anomaly. It's not EEG data, it's quite high amplitude. So, and what we can do, it's probably the best way just only remove, because how we can see, it's probably just about 250 samples. It's about 1 second of recording. We can remove this data from all channels, or thinking about how we can implement some signal processing if it's necessary, if some channels have some important information in this case, or probably in the first channels also have. And let's move forward. Now it's correlation matrix. It's quite interesting because how we can see it's quite easy implement this graph. It's demonstrate correlation between channels. So for example, we can take one channels and see how strong correlation between one channels and second channels. In this case, it's quite poor. Between one channels and third channels, it's already better, and quite similar between 1 and 7. And generally, for example, if you locate electrode in some position with your hand, and you clearly know that it's directly some correlation between some future extraction moment and this position of electrodes, you can find correlation between these electrodes and another of electrodes. So, for example, one electrodes correlated with 7 electrodes, you can just only leave these electrodes and